So, are there questions from last time? Okay, so silence means you don't have. So let me just go on. So we were discussing about this Kuramoto model. Where did we stop? Okay, I think we were here. Okay, so there was one question somebody had asked, and I think I explained it to him. How come psi, the average phase, takes up a time independent value? How is it plausible that such a thing happens? So maybe I'll just go over that argument, whatever I gave it to him. So this was the equation of motion. This we said can be rewritten in terms of the order parameter t to the I psi t thus looks like this. And we said that this one looks like a mean field system. Every oscillator is, every limit cycle oscillator is evolving in time in presence of a global field R and psi contributed by all the oscillators. Still, I saw at the end of yesterday's lecture that some of you are confused about the this frequency and the frequency that you eventually observe, the observed frequency, so to say. So, how many of you aren't yet convinced about it? So I can just go over that you aren't convinced that there are two frequencies. Okay, so let me see. So what is this guy and what is the one that you will measure? Okay. So what are these omega i's? So this is, let's say, oscillator 1, this is omega 2, this is omega 3, omega 4, etc. So these are time independent real numbers. Okay. They are taken from some distribution, but they don't change as a function of time. Something. Okay. They do not change. Okay, this one, this one has got some mean frequency and some width and so on and so forth. So these ones don't change as a function of time. But suppose you want to know, what is the frequency that you will observe if you do the experiment or if you do numerical simulation. Are you going to observe these frequencies or some other entities? First of all, observe meaning you see with your eyes. So which one will you get to measure in simulations? These frequencies or something else? See, these frequencies are hidden. No, you cannot. What you will have is, if you run the dynamics on a computer, at the end of the day, you will know how theta I changes as a function of time for all the thetas, for all the i's, right? So you know how theta 5 changes as a function of time, theta 7 changes as a function of time, and so then for these, from these trajectories, you may ask, how long does it take? Let's say I fix my time and I ask the ith guy, how long does it take to come back to its initial value? Or whatever, this initial value is unimportant. So you choose a value and you ask how long does it take to come back to that value. So this one will give you the observed frequency. This is what you would observe. So let me call this guy omega I. And this omega I doesn't have to be equal to omega I, that omega I. Need not be. It would be the same when when these two numbers would be the same? When they are uncoupled. But when they are coupled, this is the guy that you will observe, not these ones. Because you see, these ones, they are there in the equations of motion, but there is another term that expresses or that describes the influence of the other oscillators on this case. So therefore, at the end of the day, when you have the theta I data, from that you are going to conclude about the observed frequency. That has little to do with the actual frequency, especially when k is not equal to 0. Okay? In principle, yes, but then if you go to a synchronized phase, then okay, so let me just come to that. What is the observed frequency that you will get? Okay. So this observed frequency, so one way to see it is to come back to this equation of motion and see what is this observed frequency, what will this frequency be like. Now suppose I want to know how does the the average angle changes. So this is the change of the ith angle or ith phase, and I want to know how does this guy change, namely this quantity. So at any instant of time, I mark the location of the different oscillators, the different angles, and I take its average. Okay. So how I want to know how does this guy change as a function of time. So how do I find this out? What do I have to do? Given that this is so, what do I do? Or I just take the sum, which is easier, okay? So if I do that, then I get, well, the derivative of a sum is the sum of the derivatives, so therefore it's okay. This is the 1 over n here. So this term will give me 1 over n summation over omega I, plus there will be the second term which will give me summation over I comma j equal to 1 to n of sine theta j minus theta I. But now I claim that this term is 0. Do people see why this term is 0? When I sum over only one of the indices, it is non-zero, but when I sum over both the indices, it becomes 0. Nothing to do with synchronization, but something to do with the sine function, the way it is written. Why is it 0? Why would it be 0? Because you see it's an odd function, no? So ji theta j, when you do the sum, you will get terms theta 1 minus theta 2 and theta 2 minus theta 1. But sine of theta and sine of minus theta differ by a minus sign. So therefore this term will be 0. Okay? So therefore you will be left with, is this clear? I mean, this is, okay. So this is, this sort of interaction is what is known as reciprocal interaction, that the interaction felt by the ith guy due to the jth guy is negative of what the jth guy feels because of the ith guy. So they are consistent with the Newton's third law of motion, that Fij is negative of Fji. So therefore this term goes away, so I am left with just this term. So let me just then erase the second term here. And in the limit n going to infinity, that in the limit when n is very large, can you tell me how does this guy, can I write something for this guy in terms of some characteristic feature of this g omega? There's something called law of large numbers or something. No, it can't be equal to 1. Okay, because these are, these frequencies are not numbers of order 1. They can be anything. I mean, they are just sample from this distribution. Like anyway, so if you do not know, so in the limit n going to infinity, this would be just the mean frequency, which is omega naught. This is the, the law of large numbers. You take n random variables. How many of you are, now I may ask the positive question, how many of you are familiar with the law of large numbers? Okay, so a good number I would say. So law of large numbers says that for IID random variables, if you take the sum, these are IID random variables because independent and identically distributed, because for every oscillator I pick this number independently from this distribution. So they are independent by definition, identically distributed because they are all distributed according to the same parent distribution. And then the law of large number says that with probability 1, this guy, this sample mean, what is known as sample mean, will approach the actual mean, which is omega naught. So this would be in the limit n going to infinity will be omega naught. So if you don't know this, so maybe I don't know where to. I mean, I learnt it from Feller, but maybe there are better, simpler textbooks. Maybe Feller is. Mateo, I mean, like, where can they read about law of large numbers? Wikipedia, maybe. But some people here do not know.
Those who don't know, they ask either to a student from the master
or
diploma student. They know very
Okay. So those who know, they are going to teach those who do not know, and this will be a test of how much they know. Okay. So you see that the average phase that is going to if I take the ddt of it, so that becomes equal to the change of the average phase will be given by the parent frequency. Okay. So therefore, what I was saying yesterday, whenever I talked about this psi becoming time independent, what happens is that you may always co-rotate. That is, you can go to a rotating frame which is rotating with frequency omega naught with respect to an inertial frame. And then of course, this omega naught you can get rid of. You can just set it equal to 0. It's a Galilean transformation. I guess you know, right? I mean, it's quite simple. So what it says is that, what this guy says is that, this quantity, it changes with time according to a constant quantity. Okay, so the average of the thetas changes in time according to that mean frequency. So what I can do is that I can go to a frame which is moving with that mean frequency, and then of course the average will not change. Which is to say that I can set this omega naught to 0. So from this one I can just shift it and go to a distribution which has got a mean 0. Okay, so let's say for Gaussian it would look like this. So which is what I was doing here. So this is the way to set psi equal to, psi will be time independent and I can set it equal to 0 by going to a co-rotating frame. By the way, I rubbed off the observed frequency part. So the synchronization is what you see in these observed quantities, the quantities that you observe, the thetas that you observe, you see that the thetas change in time, maintaining a constant phase difference among themselves. And so then if it changes if they change maintaining a constant phase difference, we say that the system is synchronized, phase locked. I mean, this is another. So then what I can do is that I take this equation and in the stationary state, I think this is where we left off yesterday, that your equation of motion will be like this, minus kr sine theta I. Psi t I can set to 0 and r becomes time independent. And now I need to find out the stationary value of r, the time independent value of r. And as we argued yesterday, it has to be done self-consistently. because r is defined by the thetas, but the thetas in turn are determined by the r's. So therefore, it has to be done self-consistently. Okay. Okay, so the first step is to define this quantity rho of theta omega t, theta omega, because we are in the steady state or stationary state. So what does this guy tell me? It tells me of all oscillators with frequency omega, what is the probability density of finding an oscillator with angle theta. Okay, so this being a probability density, of course it is normalized to unity. And also it is 2 pi periodic in theta, because theta is a phase-like variable. Sorry. That is one. Secondly, we discussed a little bit, these are solutions of the, let me not write it again because we already discussed. You write down the continuity equation that gives me the time dependent probability, and this is the time independent solution of that equation. So what I need to do is I need to solve for this equation. I need to solve for this quantity, find out what it is. So let me just recall. So yesterday we did this small exercise, omega minus a sine theta, to say that if omega is larger than a, then the system doesn't have any fixed point. When omega is smaller than a, then there are two fixed points, one stable and one unstable. So the stable fixed point satisfies this equation. Theta omega is equal to sine inverse of omega by a, and cos of theta omega is equal to plus square root of 1 minus omega square by a square. And when omega is equal to a, then there is a half stable fixed point at pi by 2. This we did yesterday. Okay, so we are going to use this knowledge here because these two equations look quite similar, excepting that here a is a constant and there k is a is kr. So r has to be determined self-consistently. So the first thing that we see is that let's say, let's ask the question, what happens when r is equal to 0? So when r is equal to 0, then this equation is d theta I dt equal to omega I. So it just means that the oscillator phases are uniformly spread out in 0 to 2 pi at any given instant. Of course, they are moving as a function of time, but if I take a snapshot of the oscillator phases, then at any given instant I will find that they are uniformly spread out because each one of them is independent. I mean, there is no interaction between one and the other. So therefore, can someone make a guess as to what would be the form of this function? R is 0. R is 0 because the points are uniformly spread out in 0 to 2 pi. So therefore, what will be the form of this probability distribution? 1 over 2 pi, right? That is to say that you fix my omega, all theta values are equally likely, uniform distribution. So therefore, why do I get this 1 over 2 pi? Maybe not this side, but maybe some of the more enterprising ones can answer. How do I get? Can you make a guess? Why do I get it as 1 over 2 pi? There is one equation here that makes me conclude that this factor has to be 1 over 2 pi. Which is the equation? Is it this one or this one or this one or this one or this? Oh no, this is the one that we are after. Normalization, absolutely. Because all theta values are equally likely. You take a snapshot, all theta values are equally likely, and it has to be so. There is no other. And it is consistent because if I use this equation and find, you recall the definition of R in terms of this density, The definition was that what I do is that I fix my omega and I ask how many oscillators are there, what's the fraction of oscillators with angle theta. So that is rho d theta, each one will contribute a factor theta, but then I need to integrate over all possible values of theta and omega, which is this. And this is fine because if you put it to be 1 by 2 pi, then something is wrong with this equation. What is wrong with this equation? Okay, let me not give any hint. Something is incorrect about the way this equation has been written. Now, first of all, is it really the defining equation? Do you agree or disagree? Oh, actually, like even before that, I mean, something is wrong. I mean, mathematically, something is incorrect about this equation. It cannot be so. Come what may. No, this is, I am in the steady state, so the initial one doesn't matter. I am in the long time limit. Huh. Absolutely. This is a complex quantity and this is a real quantity. So something must be wrong here. And what is wrong? See, what I did was I set psi to be equal to 0. So if I set psi to be equal to 0, then I have to ensure that the imaginary part of the right hand side is equal to 0 also. Okay? And that you can easily check. For example, for this guy, what will be this imaginary part? It will be the average of sine theta, which is 0. Okay? And the real part will give me cos theta, and that is also equal to 0 if I plug in this form. So everything is consistent. There is no problem here. Huh?
Why are we also integrating over g of omega if omega is close to 0?
Okay. It is the way we are defining the distribution. So let's see. How do I define the distribution? It has, so this one says, I fix my omega, that is, okay, so I have these groups of oscillators, quenched of course, okay. So this group of oscillators has got the frequency value equal to omega 1, omega 2, omega 3, omega 4 and so on, fine. I've decided to group the oscillators according to their frequencies. And of course, an oscillator in this group cannot jump into this group, obviously, because the frequencies are pinched. Now I am asking, see, the way I've defined it is that I go to a group of oscillators that has got frequency omega, and I ask, what is the fraction of oscillators contained in this group that have got the phase value between theta and theta plus d theta. Okay? So therefore here in defining this I have fixed my omega. That is I am asking for the omega-th group. What is this one? But then when I need to compute this R, I need to first average theta with respect to this group and 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 take the sum, right? Because what I will do is that, see, what is the quantity that we are after? We are after this quantity, RT to the I psi t is equal to 1 over n. This was the discrete equation. So I can break this sum into two parts. One part is I first go to this group, I find out what is the average value of e to the I theta, taking into account only these oscillators. Okay? So this will be a function of omega, this guy e to the power I theta omega 2, e to the power I theta omega 3 and so on, right? And then I need to take the sum, need to take an average over all these groups, that is take the sum of all these contributions. That's why you get a g of omega there. Okay? You can define this distribution in another way. You can say what is the fraction of the total number of oscillators that have got angle theta and frequency omega. I am not doing it that way. Huh?
Based on how we are talking about these probabilities, isn't the rho we are considering rho of theta conditioned?
Yes, it is conditioned. So that's why I don't do it, because traditionally I should have done it, but typically people. So that's why I kept on saying, of all oscillators with frequency omega, what's the fraction that have got the angle theta? So that's why I did not cheat. You see, I cheated in the sense that I did not put this line. Somehow, when you in the literature, somehow they don't do it. I don't know what is the reason. I mean, first time when I encountered, I also thought the same way that you are thinking now. That why don't I put on this, and then then everything is fine. But okay, I don't know why they don't do it. Maybe there is a history. No, probably the reason could be the following: that the first person who wrote it down was too lazy to put this one, and then it percolated and spread from one generation to another. Because every generation thought that the previous generation must be correct, and so therefore that's the way it works. Instead of correcting it, you say, "Oh, they must be right." So that's. So you understand why you get this g omega d omega? Because you fix your frequency and then you define your d theta, but then now you have to take the contribution of the different frequency values. And how many oscillators are there with frequency value like omega? What is the total, what is the fraction of the total number of oscillators for which the frequency value is omega? That is g omega, right? Because g omega is the probability distribution. Yeah. Okay. Okay. So what we want to do is we want to see what we can conclude about that dynamics knowing these solutions. So r equal to 0, we have already found out what is the stationary distribution. It's just a uniform distribution, and correspondingly r is equal to 0, like everything is fine there. Now we need to go to the case r not equal to 0. What happens when you don't have a synchronized, you do have a synchronized solution, sorry. So when r is not equal to 0, then of course I have to solve that equation, which is d theta I dt equal to omega I minus kr sine theta I. But from our analysis here, we see that those oscillators for which omega I mod is less than equal to kr, for them the theta I will be whatever is the corresponding stable fixed point, which is fine. Because so what I do is that I look at this equation. R is a quantity that I do not know yet. I will find it out later, but I'll find it out self-consistently. So I'll pretend as if I know the value of R. And later on I'll check that the value that I pretended to know is the one that I find out at the end. Okay? So therefore I can take this guy as a known quantity, and later on and assume a value for this quantity, and later on I'll check self-consistently that the value I assumed is the one that comes out of the calculation. Okay? So if I know this quantity, the value of this quantity, then I just compare with this one. When omega is smaller than a, then the system settles into a stable fixed point. If I run the dynamics for a very long time, then the thetas will just go into, the theta value will just settle into the corresponding stable fixed point value. So therefore for those oscillators that satisfy this condition, okay, this is a time independent number because I am in the stationary state. I do not know the value, But so what? I know that it is time independent. So what I can do is that in the stationary state I can go oscillator by oscillator and check if their frequencies satisfy this condition, and if their frequencies happen to satisfy this condition, then I know for sure that their theta values would be pinned to the corresponding stable fixed point value. Okay. So for this one, can somebody guess what would be? So these are the ones which are known as the locked oscillators. These are the oscillators for which thetas have gotten locked into this value or pinned to that value. So for these oscillators, rho S is locked, theta omega, what it would look like, the distribution, how would it look like? I know that for these oscillators the theta value have gotten pinned to that value. So what would be the form of the distribution? Delta function. Let me see. Where did I write it? Yeah. Right? But then there will be some oscillators for which this condition won't be satisfied. For them what is going to happen? Well, these are the oscillators which are in this group. Omega is larger than A, so they don't have any fixed point. So their theta values cannot, there is no value for them to settle into. So their theta values will keep on changing as a function of time. But then something will happen, namely that although their theta values will keep on changing as a function of time, but let's look at the equation of motion. Okay, this is the equation of motion. Okay, although their theta values, the ones which are not locked, their theta values will keep changing in time, yet they will spend more time around those theta values for which d theta dt is small. So I pick my fifth oscillator, I plug in the frequency value here and the value here and so on, and I find that there will be some theta I values for which the oscillator will spend more time. Why? Because the velocity is small. Why? I mean, this is what we had drawn yesterday, no? That if I draw this d theta dt as a function of theta for omega greater than a for this case, and you see here the velocity is small. So therefore at those theta values the particle will slow down, and at these theta values the particle will zap through. Okay, so it's like zap and then it slows and then zap, and then you must have seen this, you know, when you have a cursor. I don't know whether it is run on the same algorithm, but you know, when something is, you know, you browse something and the page is loading, you see that there is this like arrow that goes around, and if you look at it carefully you will find that it doesn't go around uniformly, it kind of does this. So there are some regions, some theta values for which the motion is very fast, and some other theta values for which the motion is slow. And it's because of this that, you know, if you are around this theta value the velocity is small, so therefore the phase is going to spend a lot of time there around those theta values, while here it will just you know, no time, it will just go around. So therefore if I, for this group of oscillators which are not locked, okay, sorry, I have to give them a name. I gave name to the other group, so I have to be a fair person. So these are known as locked oscillators. So these are known as drifting oscillators. They are not locked. Drifting oscillators. So for them, the theta values keep on changing as a function of time, but then there are some theta values for which these oscillators are going to spend most time, and so therefore if I take a snapshot of the system, let's say, so you remember I we had decided is to represent the oscillator phases as points on a circle. So what I will find is that if I take a snapshot, what do I find? If it so happens that, and I'm talking about the drifting oscillators, the points corresponding to the drifting oscillators, each point spends some, some more time at certain theta values and some less time at like other theta values. So what will, if I take a snapshot, what do I see? I will see that, if I take a snapshot, since the points are spending more time at some theta values, so I will see that the points have come close together at those values, and the points at which the theta values at which the points have decided to spend less time, there won't be much clustering there. Okay? So therefore, it is fair to assume that for these oscillators, which are known as drifting oscillators, not just fair, this is actually correct to say that this guy will be what? Can you tell me? If I look at the density of oscillators, how can I write this down? Yeah. Absolutely, the velocity, inverse of the velocity. Where the velocity is small, you get a higher density. Where the velocity is high, you get a lower density. So you get 1, okay, there has to be some normalization constant divided by omega minus kr sine theta mod. You have to take the mod, okay, because otherwise it's a probability density. Okay. Huh, 1 minute. Why you are not taking the unstable fixed point? Is that the question? Yeah. See, you see the unstable fixed point, you will never get there, because even if you get there, you will be pushed out. That's why it's unstable. Think of it this way, that you have maybe a double well potential. Okay, so which is a stable fixed point and which is an unstable fixed point? I mean, which point will be stable and which point will be unstable? This is what? Top one. Okay, so this is what? Unstable or stable? Unstable, right? And these two are stable. Okay, so therefore, wherever you start out from, eventually you are going to land into these 2 points. Okay, even if you get there, I mean, it's not forbidden to get there. Okay, but even if you get there, you will be pushed into either this or that, because it's unstable by definition. So therefore, whenever you have so the lesson to take away is that whenever you have a nonlinear dynamical system and you find out that it has a stable fixed point and an unstable fixed point you don't care. I mean, if you start exactly at that unstable fixed point, of course you remain there. If you start exactly at this point, of course you will not move. You have to do some perturbation. That's why stability is defined always in terms of perturbation, some small kick that it gets. Okay, but this point I don't care, because there will always be perturbation. Why? I cannot just stay there forever. Why? Because the dynamics will not allow me to stay there. Because something will come in and then I'll go out. I mean, then okay. Or let me put it this way, I mean, actually the dynamics will allow me to stay there if I am at exactly at this top point, but still something will prevent me to be there. I mean, you say that it's it's like in the set of initial conditions, the initial condition that corresponds to this particular value is what? Since you know probability theory, you say something, no? Maybe that is another way of putting it. You see, of all possible initial conditions, this is one very specific initial condition. So you say that it's an initial condition of measure 0, because you will not be able to do it. You will have to do it by using a computer that has got what? What will allow you to get to exactly the top point of exactly the fixed point value. So computer of what precision? What? Infinite precision, which is impossible. Any finite precision means that there is some perturbation and you will go away. Okay. So therefore, I am not interested in this point at all. Coming back to your question, see, unstable I don't care, because I want stability in life and in physics also. So, okay. So this part is clear, the first part is clear, this is the locked oscillator, and this is the contribution for the drifting oscillators, the ones which are drifting away, but then they are drifting away but not uniformly. There are regions at which they seem to spend more time, and there are regions where they seem to spend less time, simply because the motion is not uniform. Okay, so we have been able to find the contribution of the drifting oscillators, for the probability density of the drifting oscillators as well as of the locked oscillators. Are we done? No, we are not done, because we do not know what is R. So we have found these quantities in terms of as yet undetermined quantity, namely R. So what I will do is that now I will plug this into the expression for R, and then on the left hand side and on the right hand side I will have the same quantity R, and then I will solve it self consistent. So that is the deal. Okay, so let us see how do you do it. So I guess some students, a good number of you, a significant fraction of you know about this self consistent analysis, right? You must have done it in which context? Curie-Weiss model, maybe the mean field model of magnetism, you must have done it, or okay. So what I will now do is to plug this expression into the expression for R and see. So I need to consider two such integral. Okay, so let me see, d omega d theta g omega e to the I theta of rho of SS drifting theta omega. Okay, and I have to do this. So this is drifting, means these are the ones for which omega mod is greater than kr, and the other group is when omega mod is less than kr, then I have to do this. Okay, and if I take this plus this should give me r e to the power I psi. We should self-consistently find out that psi equal to 0 is a solution. Okay, so now what I claim is that the contribution from the drifting oscillators, which is this guy is equal to 0. How do I do that? For that I need to use a symmetry, which is that rho SS drifting of theta plus pi minus omega. See, this part is algebra, so I cannot. Theta omega. How can I check that? I forgot, I probably erased off the drifting. That was equal to C divided by omega minus kr sin theta. You can check easily that this guy, you take this guy and you shift theta by pi. So if you shift theta by pi, you get a minus sign here. Okay, because sin theta plus pi will be sin theta cos pi, so this will get a minus sign here. So then this one I claim that this is the same as this thing. Do you see how does it work out, or why does it work out? Symmetry argument. Suppose I shift theta by pi, okay, so I get a minus sign here. So minus minus makes it plus. But then I say that like omega I can replace easily by minus omega, and then I'll get the same distribution. How can I replace omega by minus omega? Why do I do it? I mean, how can I do it that way? Huh? Distribution of omega is symmetric. Why is it symmetric? Because I have shifted out the mean. No, so what I did was I took this g omega distribution. There was a mean, but I shifted out the mean. So therefore, it satisfies this condition: g omega equal to g minus omega. Okay, I am talking about unimodal distributions, not bimodal. Okay, unimodal. So there is a I have shifted out the mean, so I can do. If I change sign here, I may as well change sign there, and then I find that this symmetry is respected. And if this symmetry is respected, you can easily check by doing this integral. You just shift theta by theta goes from 0 to 2 pi, like omega goes from minus infinity to plus infinity. You can check if you plug in this symmetry that this term will give you 0. Okay.
This condition is also clear to me, like g omega is equal to g of minus omega. So g omega depends on like oscillators that we choose randomly with omega frequencies. You could have chosen like some sort of Maxwellian distribution when you shift it to 0, but
No. So that's what I'm saying, that I'm specifying, I'm considering a special class of frequency distribution, unimodal distribution, which are symmetric about the mean, and then it decreases in some manner. Maxwellian wouldn't qualify as a distribution which is symmetric about the mean. Yeah. So then this term goes away. So I am left with only the second term. So I need to just find out the second term. So this integral, what you have to do is that for the locked one, you have to just plug this guy here, the delta function, and the delta function integral is very easy to do. You d theta and you do some, change of variable, etc. It's all worked out in the notes. So let me just skip that and come to the final answer. So the final answer looks somewhat like this. R equal to KR of minus pi by 2 to pi by 2 of d theta cos square theta, and you will find that psi equal to 0 self-consistently satisfies the equation by using the symmetry properties that we just mentioned. So now we have arrived at the desired self-consistent equation. So R was determined by the rows of the densities of the locked and the drifting oscillators. The drifting oscillators don't make any contribution, and so therefore, and it is quite natural that the drifting oscillators don't make any contribution, no, because they will just cancel away. The contribution will just get cancelled away. While the locked oscillators are the ones that make a contribution, and if you do this integral, you get this equation. Yes, so that this is the self-consistent equation. See, okay, so let me see. See, rho SS, either drift or locked, doesn't matter. Let's say locked. This had this form, theta minus sine inverse of omega by kr. So the distribution is determined in terms of R, but I don't know what R is. So what I do is that I take this, assume R to be known, I plug this into the expression for R, I get this self-consistent equation. So what I need to do is, it's like a transcendental equation, no, x is equal to tan x or something, that I have to find an r cannot be any arbitrary quantity, it constrains the value of r. For example, one thing I can easily see that r equal to 0 is a solution. Yeah, because if you put r equal to 0, then everything, it just works out, because g0 will be some constant number, it does not depend on theta, because g0 is the value of the distribution, the maximum value of the distribution. So this will give me some constant, 0 to pi, sorry, minus pi, this is a cos squared theta. So this is some finite number. So therefore finite number times 0 is 0, and on the left hand side also I have 0. But the problem is r not equal to 0, like, is it a solution? No, it does not always have to be a solution, okay, because it will be a solution, but then it will put some constraint on the value of k. Not always r not equal to 0 is a solution, and therefore we will get the value of coupling beyond which the system will show synchronization. Unsynchronized state is always a solution. We will see that it becomes unstable and so on, but the synchronized state is not always a solution. It will be a solution provided k is larger than some value and so on. Yes, indeed, yes. So what I will do is that I will, so let's see. So if I plot r as a function of k, this is the picture that will emerge, that there will be a critical value above which r not equal to 0 will be a solution. So the way to find this point is to approach this point from the upper side, from the right. So that is to say, I evaluate this equation as r goes to 0 plus. But before that, I mean, since I did these calculations in sort of a rush, so let me just pause for 2 minutes and ask, do you see what am I doing? Why am I doing, I want to check whether this model shows synchronization. But why am I doing whatever I have done? Do you see? So think and let me know while I drink some water. So you understood what we are after. We want to check whether in the stationary state the model allows for a synchronized stationary state. That is, does it allow for a non-zero value of r? That is why we want to compute the value of r, and the way to compute the value of r is to know the form of the stationary distribution, because r involves an integral over the stationary distribution. So then the first thing that I need to do is to find out the form of the stationary distribution. The second thing what I said is that the stationary distribution can be easily found out for the locked oscillators, because these are oscillators for which omega is smaller than a, here a is k of r. So these are oscillators for which the theta values would get pinned to the corresponding stable fixed point value. Okay. So for the locked oscillators, rho SS locked will be basically a delta function. The third thing is the form of the stationary state for drifting. These are the two varieties, either you are locked or you are drifting. You may drift to lesser or greater extent, but a drifting oscillator is a drifting oscillator, and similarly a locked oscillator is a locked oscillator. You cannot. So the drifting oscillators, these are the ones for which there is no stable fixed point. They belong to this variety, this group. Omega is larger than kr. So for these drifting oscillators, there is no stable fixed point. Yet, how can I make a guess for these for the form of this probability density, what I can say is that although they are drifting, but they are not drifting uniformly around the circle. There are certain regions in which they seem to be drifting very fast, and there are certain other regions in which they seem to be drifting very, very slowly. Why? Because the velocity with which they drift, which is d theta dt, so that depends on the angle. Okay, like had this term not been there, they would have drifted uniformly. But then, since this term is there, so there will be some regions in which the difference between these two guys will be small enough to slow them down, and there would be other regions in which the difference will be large enough to speed them, to make them speed up. Okay, so the drifting oscillators, therefore, they have a density which is inversely proportional to the local velocity. This up to this everything is clear. This one is quite easy. I mean, this one is a bit tricky, but only a bit, not too much. Huh.
Like, this is the simplest thing we've come up with. Can we, like, bring up some a bit more complex functions to model this?
Okay, the problem is that, okay, let's see. See, you have this equation. So the what would have been the ideal thing to do? The ideal thing to do would have been to solve for this equation, where this is theta dot of rho, where theta dot, as I was saying yesterday, is this complicated function k of you can write it in terms of this, or best is to write rho of theta prime omega prime t d omega prime d theta prime, or you can write it in terms of r and psi also, it's the same. So the ideal thing would be to solve this time dependent equation and take the limit t going to infinity. This is the most ideal thing. Next thing what you may say is that no, so what I do is that I set this guy equal to 0 because I want to know the steady state velocity, the steady state distribution. So then I need to solve this equation of this times rho ss theta omega, that is equal to 0. Okay, so the best that you can do is to say that theta dot rho ss theta omega. In fact, this is the probability current. No, this is del j del theta. So this would be the j stationary, the stationary current. Okay. In fact, all the forms that we have written down, they are all consistent. That is the reason why you get for the drifting oscillators j to be inversely proportional to theta dot. The constant that I had written there is c. Okay. And for the other ones, what would be the current? The locked ones, what would be the current? Current would be just 0, because they are just stuck there. No, I mean the co-rotating film, they are just stuck there. So therefore, for them you can easily check if you put JSS equal to 0, the form of the locked oscillators that I have written down would ensure that this guy is equal to 0. Why? Because this guy is what, delta of theta minus theta dot. So therefore theta dot has to be 0, which is consistent. Okay. So what I did was I skipped this part because I sort of thought that it would be easier to motivate it from physical grounds, but you can also do it mathematically the way I did it, that you write down the equation of continuity, you set the left hand side equal to 0 to get the stationary distribution, and then you get this equation del del theta of the current equal to 0, which is to say that theta dot times this is equal to the stationary current. Now the stationary current can be either 0 or non-zero. By definition they are 0 for the locked oscillators because they are just stuck there. So this is stationary current in theta. The current is coming because if I look at a small interval in that circle, points come in and go out. That's why there is this equation of continuity. Okay, there is a current of, not current of chalk, only one chalk. Anyways, I didn't mean it, it just happened. So things come in and go out, but for the locked ones there is no possibility because they are locked and cannot move. So therefore, the locked ones will contribute a zero current, and you can check from the form of the locked oscillator distribution that I have written down that this is equal to 0 is satisfied. For the other ones, the drifting ones, surely they are drifting. So if I look at one small interval, I see that points come in and go out continuously, but then the current is the same. I mean, it is time independent. Okay, it may depend on where you are measuring the current, but it cannot also. Why? Because in the steady state it will be the same current that goes round and round. Okay, so it is independent of theta and independent of time, and it is independent of theta. It better be so, because otherwise this del theta would not be 0. Okay? And then you see that for the drifting oscillators, the density will be inversely proportional to the velocity. What is the velocity? Velocity is nothing but omega minus k r sine theta. Right? So that is why, for the drifting one, 1 by theta dot, which is this. Okay, how many of you understood the conversation that we just had? Like, even if you, okay, ideally I would like that you get the conversation that I just had. But even if you don't get it, I mean, this is a more rigorous way of doing it. But then for this, you have to know a little bit, how does this equation of why does this equation of continuity come into picture, and what does it mean, and so on and so on. It's a bit lengthy way, but not too complicated. Okay, so I think I better get going. So that's why I said, okay, so I found the form of the locked oscillators, I found the form of the drifting oscillators, and I find that both these densities depend on the quantity R that we do not yet know what it is. So what I do is that I take these expressions for the densities and plug them back into the equation determining R, and that gives us a self-consistent equation. This is what is known as a self-consistent equation, that this R cannot be any arbitrary quantity, because it has to satisfy both the left hand side and the right hand side. So typically what you do is that if you get an equation of this sort, what do? How do you solve it? I mean, let's say I give you some value of k is equal to 525.762, and g omega, so this function is a Gaussian. So how will you do it? Typically, how do you do it? Okay, you plug the value of k here, you do this integral here, but then what? I mean, R is undetermined, you don't know what the value of R is. So how do you solve such equations? Graphically, right? I mean, what you do is that you put a value of R, so this one will give you a straight line, and this one will give you some curve, and then you see when they touch, intersect each other. So that will give me the self-concept. How many of you have seen this equation? M is equal to tan hyperbolic beta Jm. And I don't say what beta is and J is and M is, but I just ask how many of you have seen this equation? Okay, so I was expecting a larger number. Anyway, so this is an equation of the same sort. This is a nonlinear function. This is the equation determining the equilibrium magnetization of a mean field model of spins, the Curie-Weiss model. Curie-Weiss model is like this. Okay. Or this equation also arises when you try to solve the one-dimensional Ising model in the mean field approximation. And of course, do you get good answer, like the answer that it gives you, like does it match with experiments? The mean field approximation answer? No, yes, I mean it just predicts that there is a non-zero phase transition at a non-zero temperature at 2J by, what is it, 2J by KB, yes. But in 1D Ising model with short range interaction, you cannot have phase transition. This one will show phase transition, this is a mean field model, okay. Okay, so let's come back to this equation. By the way, since I mentioned about Ising, let me just make one small connection with the XY model, Kuramoto model with the XY model, because that may, you may be tempted to think that is there some connection. So this one, Okay. So this term I can interpret it as minus del v del theta I. Okay, that so for the moment forget about the frequency term. Okay, so those of you, I am told that in this PCS program you know a lot, so perhaps you already know this one. So let me just say that so first of all let me ask, okay, Ising model or XY model etc. I mean, do they have a dynamics defined for them? I mean, okay, these are spins, they are interacting with one another, there is a Hamiltonian given to you, but how does a configuration of spins evolve in time? What do you do? Does it evolve? It has to evolve, no? Because, okay, you start with all spins up, let's say 1D Ising model, and you want the spins to, fluctuate, go up, down, down, up, down, whatever. So how do you build the dynamics there? So simulation, so you have to tell the computer what are the rules. So what guides you as to what should be the rules of evolution? No, I heard something. Why would it, how would it decrease the energy? And then I'll ask why would it decrease the energy? Why do you do it? I mean, I may come up with my own algorithm that if I flip and if it increases the energy, I accept that configuration. Okay, so because I don't have much time to get into that. So what happens is that you see, you want to get to an equilibrium stationary state, e to the minus beta h. So therefore your dynamical rules of evolution have to satisfy detail balance condition. And detail balance tells you that the way to go from one configuration to another, you define a transition rate that says I go from this configuration to this one, to this one, to this one in such a way that the detail balance condition is satisfied. And there are many choices. Glauber is one, Kawasaki dynamics, Metropolis, heat bath algorithm, etc. etc. And why would you like to decrease the dynamics? Because decrease the energy, because it's an overdamped dynamics in an energy landscape. So you want to get to the minimum of the energy. Okay. Minimum of the free energy more precisely, because there is a free energy landscape, and statistical mechanics, equilibrium statistical mechanics tells you that when you are in contact with a heat bath at temperature T, the equilibrium configuration is the one that minimizes the Helmholtz free energy. So you want to minimize the free energy. So therefore when you flip the spin, if the energy decreases, then you necessarily accept that configuration. If it increases, you accept it with a smaller probability. So that is to say, the equation of motion, if you write down the equation of motion for these variables, for the moment forget about this guy, it would be of this sort, plus eta I, a Langevin equation of this sort, where V is the potential, and as you can guess, if this is the force that is appearing, the potential will be, and you will at once realize what sort of potential it is. This should be a square bracket. So if you take this potential and if you take the derivative with respect to theta, you get this term, and your dynamics looks like this. There is no eta here because this is a nonlinear dynamical system. There is no heat bath in which the system is kept in contact and it is evolving like that, okay? But more generally, if you have a heat bath, you have a term of this sort, and this is an overdamped dynamics. I hope you know Langevin equation. I am told, Edgar has told me that the diploma students should also know what a Langevin equation is. So this is a Langevin equation, okay? And then what happens is, can somebody recognize what sort of potential is this one? What sort of spin model would generate a potential of this sort? Cosine of the angle. So these are two-dimensional vectors, no? Because you think of the ways we have decided to depict the points. These are like points moving on a xy spin. Indeed, this term you can easily write it as SI dot Sj, where SI is cosine theta I, sin theta I, and similarly Sj is cosine theta j, sin theta j. You take the product, you get exactly that. The new thing is this guy. This guy makes it horrible. See, this frequency term you don't have in equilibrium, because it seems as though every spin has been endowed with a frequency. So the spins are rotating under interaction among themselves, but also every spin has been subject to a drive which is different for different spins. And I have taken away the effect of the external heat bath. So then this model becomes like this, and in fact we will see tomorrow that if you include the noise, and take away the heat bath, then you get to an equilibrium stationary state of the system, which is nothing but the equilibrium stationary state of the xy model. But then if you include the frequency, then there is no equilibrium stationary state, then the system goes into a non-equilibrium stationary state. We will see what do I mean by equilibrium. So I am just bombarding you with words. So let us just come back to this equation and see how does one solve that equation very quickly, and then I will mention something about this Otantans and answers. Okay. So G of kr sin theta d theta cos square theta. And the picture that we have is the following, that this is the stationary value of r, this is the value of k, there is going to be a critical value below which r equal to 0 is the stable solution. Well, r equal to 0 is a solution for all values of k, it does not care, okay. But this solution is stable here, while if k becomes larger than kc, there is another solution that bifurcates from this one. That is, suddenly the differential, this equation starts having two possible solutions. Okay. So what is the way to get the value of this critical coupling? What I do is that I take this right hand side and I evaluate it as r goes to 0 plus. That is, I try to approach this critical point from this end, and then if there is a non-zero solution, I should be able to find the value of the coupling below which such a solution does not exist. Okay, like again this is also a very routine thing to do. This is how you find the phase transition, the critical point of a second order phase transition, that if there is a, this looks like a second order phase transition, the difference is that it is not a phase transition, it is a bifurcation. Why it is not a phase transition? Because you talk about phase transitions when the system is in contact with a heat bath and you get to equilibrium, e to the minus beta h is the equilibrium distribution, and you find the value of the order parameter and so on. Okay. So here there is no free energy that you are trying to minimize, you are just solving the dynamical equations of motion and finding that in the stationary state this is a solution for the order parameter, and finding out when does the order parameter admit also a non-zero solution. Okay. There is some some tricky thing that happens for this model. You may say that okay, first of all before that, okay, if you do this analysis, this is worked out in the notes. What you do is that you take this function, and since r is equal to 0 plus, r is slightly larger than 0, that is you are somewhere here, not too far but somewhere here. Here there is no point in asking for a non-zero solution of this equation, because this equation does not allow a non-zero solution. Here it does allow a non-zero solution, but then let us say the value of r that you are getting is very small, which is what is going to happen is if k is slightly larger than kc. So what I do is that I take this function, I expand it out, Taylor series expansion, considering r to be the small parameter. K does not have to be small, but r is small. So you just expand it out, and to leading order you will find, I mean you can almost see what is going to happen, that to leading order you have to take the What contribution from this guy? To leading order, if I expand this out, see there is an R here and there is an R here. So to leading order, what order in R should I consider from the integral? 0, right? Because there is already an R sitting there. Okay, so no wonder the critical coupling will be given by 2 by pi g0. You almost see where it comes from, because if you do a Taylor expansion, you take the leading order term, it would be g0, and then integral minus pi by 2 cos square theta g theta, and that gives me 2 pi. So what you would get is, you would get something like R is equal to kr kcr of g0 into 2 pi, and R is k. So can I cancel R from both sides? By pi g0, maybe there is a pi missing or something. Okay, so can I can I cancel R? I hope I wrote down the equation correctly. No, cos square theta is what? 2 by pi g0. Yeah, this is fine. So can I cancel R from both sides? Yes, because that's what I am doing. I am approaching, so R is not 0, so I can, it's 2 by pi. Sorry. Let me see. So Kc will, so R I can cancel. So Kc will be 2 by pi g0. Yeah. So I have been able to compute this bifurcation point. This is what is known as bifurcation. Those of you who know about phase transitions require thermodynamic limit, and you have a lot of things to be satisfied when you have a phase transition. It's just a bifurcation. You have a solution which is 0 here and non-zero there. Okay. Are there questions until now? So this integral, how to do the Taylor expansion and how to do this thing, these things are all worked out in the notes. So you can just, you have to just play with this integral. Okay. Acha, so one strange thing is that here R equal to 0 is the solution, here R not equal to 0 is. But we argued that R equal to 0 is always a solution. Then here I am saying that R equal to 0 is a solution, R not equal to 0 is also a solution. So what's going on? How can you have both the solutions? I mean, of course, you can have both the solutions, but if I do an experiment, which one am I going to observe? The non-zero solution or the zero solution? Non-zero, because this must be the stable solution. So what happens is that when k is smaller than kc, R equal to 0 is stable, but when k becomes larger than kc, R not equal to 0 becomes stable. But the bad thing is that R equal to 0, instead of being unstable, becomes marginally stable. I mean if you do the stability analysis, so there is a very nice discussion of how it becomes actually unstable here. What is the flaw in the argument that I just gave? There's a very nice discussion about this in the review by Strogatz, from Kuramoto to Strogatz. From Kuramoto to Crawford. And there is a very nice connection that he brings up with the Landau damping problem in plasma theory, some analytic continuation that one has to do to find out that actually R equal to 0 is stable here and unstable there, and R not equal to 0 is stable here. Just naive linear stability analysis will give you wrong answers, and why one has to do it carefully, this is all explained there. But now let me ask the following question, that this is for the steady state value of R. Can I compute the time dependent value of R? How does the value of the order parameter change as a function of time? I'll just state the result, because that will, that's much more mathematically involved than this one. But before that, is this picture clear? That what we have been able to show now, whatever we have gotten to, we have been able to show that this very simple Kuramoto model has been able to achieve what we wanted it to achieve. Namely, it has been, it has been able to demonstrate for you the fact that in this very simple setup, there is indeed a critical value of coupling beyond which the system spontaneously synchronizes. Synchronized stationary state is a stable solution of the dynamics provided the coupling is strong enough. And indeed I know that when there is no coupling, there cannot be any synchronized state. So the coupling better be somewhat strong. How strong would it be? Would it have to be? It has to be at least stronger than the critical coupling case. And we have been able to obtain an exact expression for 2 by pi g0. The solution that we worked out somewhat in this class is non-trivial in view of the fact that this is not a statistical mechanical system for which one knows a priori what is the probability distribution, Gibbs-Boltzmann, and you can minimize the free energy and so on and so forth. You cannot play any of those games here. You have to come up with, when you read this review of Strogatz, you realize, no wonder Kuramoto was given this medal for this work, because it required a lot of very useful physical insights. One has to have a very deep understanding of the underlying dynamics in order to come up with a theory that is able to predict the critical value of coupling. The last thing that I do is I ask, R in the steady state, we know, we saw what it is, okay. But what about R as a function of time? Can I write down an equation of motion for the order parameter? That would be the ideal thing to do, no? Let's see why is it so difficult, or is it easy to write down? So let's see. So I have the equation of motion for this guy. And suppose I want to know the equation of motion for this guy. So how would I do it? I just take the time derivative of the left hand side. Okay, so I will get a term dr dt, and there will be a d psi dt, and here I will get a d theta j dt, and in the expression, for d theta j dt, I will just substitute the equation from here. You see that you will get an equation that cannot be simplified, because what you will get is, you will just get e to the power I, okay, let me just do it. If I just take the time derivative, you get dr dt e to the power I psi t plus r e to the power I psi t of d psi dt. This is equal to 1 over n summation j1 to n of e to the power I theta j times theta j dot, but theta j dot is this guy. But then what do I do from here? Huh? There is an I missing. But even if you put that I, it is as complicated, and I don't know what to do with this one. So therefore, this equation, now we are not in the steady state. We are asking, how does the system approach the stationary state? Okay. So then, so these two gentlemen, Edward Ott, and I think the first name is T. Antonsen. So they came up with a very profound theory that is able to write down, they were able to write down an equation of motion for r of t only for the case in which this frequency distribution is a Lorentzian. If you take Gaussian, it doesn't work. Can somebody make a guess why Lorentzian would be easier to handle? Just to give you a hint, you see RT to the power I psi t, if I write it out in terms of the distribution function, it looks like this. And I claim that if you choose your g of omega to be a Lorentzian, then this integral can be tackled quite easily. Not quite easily, but somewhat easily. Why is it easier to have an g omega which is of that form that would make that integral easier to deal with? This function has a particular form. So something happens. If you have these functions and if you have integral over such functions, then you do something that makes the integral evaluation easy. This you must have studied in your bachelor's program. Math methods maybe. No, this doesn't seem like a Fourier. E to the I theta. You need an e to the power I m theta. So this may be just the first Fourier mode or something. No, but what I am claiming is that if you plug this guy here, then at least it should ring a bell that something becomes easier to deal with. What I can do is that so this frequency, it's a real number. What I can do is that I can analytically continue to the whole of the complex omega plane, and this has got poles at like omega equal to plus minus I sigma. So if I plug this one here and convert it into a contour integral, then I should be able to do that integration somewhat easily, which is not obviously the case if you take g omega to be a Gaussian distribution. Okay? So that's what they did, and it's a very long calculation, but it's all worked out there. And just to make you feel comfortable mastering the technique, what I've done is that I've also assigned a problem which you can solve using this technique of this Orth-Antonsen. But the final answer is a time evolution equation for this order parameter that looks quite simple, which is, this is the equation, dr dt plus sigma r minus k by 2 of r cube minus r. So these are all functions of time. Equal to 0, and the second equation is d psi t dt equal to 0. So you see that indeed in the stationary state, if I go to the stationary state, so what will happen is that dr dt will be equal to 0 and d psi t dt will be equal to 0, so psi becomes constant, and the stationary value of r that you get from this equation has to match with the value of r that you extract from here. But this equation is quite easy to integrate exactly. So I'll just write down the so let me just write the equation for r square t, which is easy. See, this is a first order differential equation in time, so its solution will depend on the initial condition r0. Okay, this is the time dependent solution for the other for this r of t, which is the order parameter. And this equation is valid if k is larger than 2 sigma. Can you guess what is this 2 sigma quantity? Like, is it related to any quantity that you see on the it is Kc, and in fact you can check using this form that if you do Kc, which is 2 by pi g0, then you should actually get 2 sigma, right, because g0 is what, it should be 1 by sigma pi, so 2 sigma. More than that, what this solution tells you is that, sorry, there should be a t somewhere. Yeah, sorry, this is t. So what this one tells you is that, okay, this one is lead for k not equal to 2 sigma. So let's say when k is larger than 2 sigma, when k is larger than 2 sigma, then what will happen to this factor? This factor. When k is larger than 2 sigma, it will go to 0. Then you will be left with k minus 2 sigma r square 0 by k r square 0. So therefore, the steady state value that you will get here will be square root of 1 minus 2 sigma divided by k, right? But 2 sigma is nothing but kc, so this would be 1 minus kc by k. And everything is fine because k is larger than kc, so it's a real number, that's fine. So what we find is that not just I have found the the time dependent solution, but I also know how does this curve look like. It looks like 1 minus kc by k for a Lorentzian distribution. So therefore, it is a rare instance in which you can not only, you are able to not only find out the critical point, but also you are able to predict the full branch of the solution. How does the non-zero branch look like? What is the equation for the branch? It is like this for a Lorentzian distribution. And you can extract a critical exponent also. Those are, how many of you have done critical exponents? Exponents at, okay, so what will be the, so the critical exponent for magnetization is what? So it is magnetization, it goes as T minus Tc to the power what? What is this exponent called? So it has a, you denote it by a particular symbol. Huh? Beta. Alpha is for specific heat. Nu is for the correlation length, and so on. Gamma is for susceptibility. Okay. So what you see is that if I, here it gives you beta equal to 1/2 for the Lorentzian case. For other cases, of course, you cannot solve it exactly. So I think I have, I had kept an eye on the time because like initially there were 10 minutes that were gone. So I think it's a good time to stop. So tomorrow what we will do is we will see what happens if you add noise to the system, and how does one go about solving the corresponding Langevin equation, Fokker-Planck equation.
Sorry, before you erase.
Shit.
This was the long time behavior of this.
Yes.
Okay.
Yeah. So the good thing is that, see, the Kuramoto analysis allows you to only get the long time behavior,
Yes.
but this one allows you to get the full time dependent behavior. The only restriction is the frequency distribution has to be Lorentzian.
I had a question
Yeah.
because I think I lost something.
Yeah.
You said something about that this is a bifurcation point and not a phase
transition point. Yeah.
Okay. And there's nothing deep about
No,
this.
there is deep about it, because you see bifurcation may take place for a single degree of freedom. You may have an equation dx dt. It doesn't require to have an infinite number of degrees. But phase transition takes place only in the thermodynamic limit.